Okay, let's see how this magic number of 2.51 comes about. And this work was done by Norman Pogson in the 19th century. If we have two stars that are the same magnitude, then they have a difference of magnitude of 0. And that means that their ratio of intensities must be 1 because they have the same number. One value divided by itself is 1. So if they have a difference of magnitudes of 5 magnitudes over here, what Norman Pogson discovered or thought about was that the ratio of intensities should be representative of 100. So one object would be 100 times more intense than another, brighter than the other one, if on the astronomical magnitude scale they had a difference of 5 magnitudes. And so we can use that fact to represent the magnitude scale. So the fifth root of 100, that's 5 as a difference of magnitude, would give us a factor relating each magnitude of 2.51. That is to say that one magnitude difference between objects would be a ratio of intensities of about 2.51. 2 magnitudes difference would be 2.51 squared. 3 magnitudes difference would be 2.51 to the power of 3, which is 16, and so on. And so that allows us to establish a scale. You've just always got to remember, though, that the scale is backwards. So the brighter object has a smaller value of magnitude. So let's write that down as a formula. Here we go. Using the 2.51 that Norman Pogson came up with, and it's called Pogson's ratio for that reason, we can write down the ratio of intensities. The brighter object is IB. The dimmer object, the object that's less intense, is IA. And that ratio of intensities is equal to 2.51, Pogson's ratio, to the power of the difference in the magnitudes. And you can see here that we've got the dimmer object first subtracted from the magnitude of the brighter object. And it's done that way around because the magnitude scale is backwards, and we want this subtraction to give us a positive number. Now, this is one good way of representing the magnitude scale, but it's not the only way of doing it. And so we're going to do some quick mathematics in order to find a new way of representing the magnitude scale that will help us later on. The thing that we might notice if we played around with the calculator for a while is that 2.51, that's Pogson's ratio, is actually approximately equal to 10 to the power of 1 over 2.5. And the reason why that's useful is because if we can represent something as a power of 10, then we could use logarithms to the base 10 to represent it mathematically. So here we go. We're going to use the idea that a to the power of 1 over b, all to the power of c, is the same as a to the power of b over c. So let's write that now. We're going to take our 10 to the power of 1 over 2.5, which we know is equal to 2.51, and there it is, 10 to the power of 1 over 2.5, and we're going to raise that to the power of the difference in our magnitudes. There it is. And so using this wonderful piece of mathematics here, we can take this formula and turn it into this one. And as I say, the advantage of that is that this is a power of 10. And that means that we can use logarithms to the power of logarithms to the base 10 to help us. Here's our next step. Let's take logarithms of both sides. So that's going to take this part of raising the power of 10 and pop it just simply on this side. And we're going to take the logarithm, of course, of both sides. So we need to take the logarithm of this side as well, and there it is. So that's another way of writing this formula. Now, of course, there's all sorts of things we can do here because the logarithm of IA over IB over IA even could be written into all sorts of different ways. But one of the nice things we could simply do is we could take this 2.5 and multiply it by both sides. Here we go. So there it is. So this is another way of representing the magnitude scale, and it's a very useful formula because the logarithm allows us to apply other mathematical rules. Okay, so what we're going to do next is to look at how we can use our new formula to look at a star from two different distances. So we're going to be looking at the same star from two different places. For instance, we could be looking at the star from Earth, or we could move up much closer towards that star, say 10 parsecs away from that star, and we could observe it from there. And if we moved up towards the star, just 10 parsecs away, then that star is quite obviously going to look quite a bit brighter because we're going to be closer. So its intensity is going to be higher. Remember, in this formula, we're using IB for the brighter object and IA for the dimmer object, and therefore the value of MB is smaller than the value of MA. Now, in order to represent the intensity, we need to know the formula for intensity, so here it is. Intensity is the power emitted by the star divided by the surface area of the sphere over which that light is spread out at a distance of r from the star. So that would give us the intensity in watts per meter squared. Now, as we move further away, we increase the value of r, and therefore we decrease the intensity. So what we're going to do is going to substitute this formula into this one twice, once for IB and once for IA. It's the same star though, so therefore the value of power emitted by that star is going to be the same. So here it is. Here is the same star and hence the same power being emitted. And then we have the distance to the star RB being at, say, a close distance, being different from the distance to the star RA. So RA could be the distance from the Earth to the star, so that's what we would observe from our position here with a telescope close to the planet Earth, and RB might be some reference distance, maybe say 10 parsecs or something like that, much closer to the star than we are on the Earth. Now, of course, the nice thing about this is that these powers are going to cancel. So P cancels, and the 4 pi is also going to cancel out here and here as well. And that's just going to leave us with 1 over RB squared divided by 1 over RA squared. And of course, those 1 overs mean that we can turn the whole thing upside down and represent it much more neatly and concisely in mathematics as RA squared divided by RB squared. So you'll notice that the nice thing about this is that now we have a formula which, for the same star, represents the difference that we will see in its brightness magnitude as a ratio of the squares of the distances, taken as a logarithm. Okay, well, we can use the law of logarithms to help us one last time. We can take the squares away here, because any logarithm that has an index inside, raised to the power of, say, 2, you can take the 2 out and multiply it in front of the log. So our 2.5 is going to be multiplied by 2 to reach 5, and we can now lose the squares from inside the logarithm because they're now represented by the 5 outside. So here it is. This is a really useful formula for showing us how the magnitude scale is going to change when we move from different distances. Now, since 10 parsecs is a standard for representing what we call the absolute magnitude of a star, we can therefore write out the formula in this form. Here is the distance that we are observing that star from, say, the planet Earth. Okay, and here is the magnitude that we observe from the planet Earth. Okay, and then this is our reference distance of 10 parsecs, and this is the absolute magnitude of the star. The absolute magnitude being a way in which we can compare stars to each other, and obviously using this formula we can make sure that those stars are all observed virtually from that 10 parsec distance by taking account of the real distance between us and that star to calculate a comparable magnitude at that distance of 10 parsecs, regardless of where we actually are in relation to that star. Of course, if this is measured in 10 parsecs here, then that means that D must also be measured in the astronomical distance unit of parsecs. Okay, so this is a formula which uses parsecs, not light years, not meters, not astronomical units. It's got to be done in parsecs. So rearranging this formula, we could get a formula for the absolute magnitude of the star, or alternatively, if we wanted to, we knew the absolute magnitude of the star, and we knew the distance to that star, then we could work out how bright we would expect it to look from the planet Earth, the apparent magnitude, which is little m there. So there it is, that's the magnitude scale for astronomy, and turned into mathematical formulae and related with all of the derivations that you need to understand how it comes about. Of course, what you end up actually remembering for your exam is going to be a smaller subset of this material. You're going to remember Poisson's ratio, how to use it, and you're going to remember this formula and how to use it.